Here I will focus on numeric library of STL algorithms. Usually numeric libraries algorithms are not categorized, but here I attempt to categorize them as query, mutator and manipulator types. Query type algorithm reads input container or the object's data from the input container and range and returns a computed result. Typically the result is in the form of a scalar value or a single object. Mutator algorithm reads the container range and modifies it in its place. It modifies the input container itself. Manipulator reads data from input container range. It could be one container, or it could be more than one container, and writes the result to the output range, output container or range. Here you see numeric algorithms categorized as query, mutator and manipulator. We have query type algorithm: accumulate, reduce, inner product, transform, reduce, GCD, LCM, midpoint. Mutator type iota, manipulator type adjacent difference, partial sum, inclusive scan, exclusive scan, transform inclusive scan, transform exclusive scan. Let us learn these algorithms, query algorithms, through coding. We consider accumulate, reduce, inner product, transform, reduce, GCD, LCM, midpoint. GCD, LCM, midpoint are utility functions that are available through numeric library that can be useful in the use of another STL algorithm. So they are not algorithm themselves, but they are utility functions that are useful for the algorithms. Let us begin coding. So as a preparation, I need to create a type. I want to demonstrate the use of the algorithms for custom type. Since we are dealing with numeric type algorithm, it's sensible to have kind of a numeric type data type or numeric type or type which actually is designed to deal with numeric data. So let me consider a class a point. Let me consider 2D point, right? So which will have double x value and double y value. So x and y coordinates, and then we have public because we have this initialization curly braces, so we can have a default constructor like this, set to the default constructor, and we can have a custom constructor point 2D double px double py and set x px y py. So this is the custom constructor, and I want to have a function that we can use to display this point data. So let me have a friend function operator overloaded const point 2D object. Let me call this p2d point 2D. So definition return OS display in a parenthesis display p2d.x and separated by comma p2d.y. So this is the function we use to display, and also I want to have a function to display a container. I will need to use that to display the content of the container several times. So let me create a template function to that will apply to all type of containers. I want this function to return OSTream object. Print call this print C constant T container. Let me call this C, and then for constant auto, call this C and T, and auto C and T. stdc out and C. It'll display the objects, the elements separated in a single line, separated by this space, and we return cout. So this is the function we're going to be using. First, let me quickly make sure that this function works. So I'm creating, to use the vector container, I need to include a vector library. I want to make sure that this function actually does the work. So let me switch to the terminal, try to compile this. I think there was a typo problem. So we have OSTream. To REAM OSTream and OSTream. Let me try again. I still missed oh, and in the end of class definition you should have semicolon. So this is the outcome. It is looks like it is working. So I will continue with this. If problem arises, I will come back and try to fix it. So we have this type and we have this function to display. Now we begin with accumulate function. To be more specific, std accumulate. This is available through a library called numeric. And the purpose of accumulate is to get the summation, right? So maybe first let me use this for integer type, then afterwards I'll create a vector of this point to d type and also try to demonstrate for that. So if I want to accumulate, let's say I mean compute the summation of all these numbers. So I could do something like this. You need to pass the iterator, first iterator IBEC dot begin, and the last iterator IBEC dot end. And for accumulation, it's like, if you, let me just explain it a little bit. If I want to compute, suppose this is a vector, right? This is a regular vector. Then if I want to compute the summation, then first I need to define int sum equals to 0, int slice to 0, and then I can iterate int I equals to 0, I less than, let's say, in this case it's going to be 1 2 3 4 5 I plus plus, and then you do summation sum plus equals to, let's say, so if IBEC were an array, it was array, then you will have this same syntax for computing the summation or accumulation, right? So the thing is that you need to provide the initial value. If you set initial value 10, then everything will be added on the top of that initial value. If typically initial value is 0, but sometimes your application may demand you to have some base initial value, so in that case you can supply something else. So in accumulation also you need to supply or pass initial value. In this case we are computing the integer type. So basically the initial value, the type of initial value has to be the same as the type of this the value to be computed. If it is double, it should be double. If integer, it should be integer, right? So in this case it is integer type. We are accumulating this integer data. So we start with 0, and you want to provide a function here. In the function you want to have these two things, this as a parameter and this thing as a parameter. Both are of integer type in this case. So we're going to have integer, call this sum, and integer you can call you can use different name. Integer is going to be value, and you return sum plus value. So it will this will actually do this kind of computation for each element of this container. So it start from 0. In the beginning sum will be 0, and then 0 plus first value, and then that first value is going to be in this sum, and that's going to be sum plus second value, sum plus third value. It goes that way, and the final computed value is going to be returned by this function. So maybe integer total equals to, and you can display it. Right, so let's see, expected output here would be 5 4 9 10 11 12 15. So total is computed to be 15. Now if you want to do accumulation of this value, which are let's say greater than 3, you want to accumulate only values. Let's say let's a little bit different. If you want to accumulate only even values here, right? In that case you can make some changes here. When you do the summation, add the value. If it is even, you add that value, otherwise you add 0 value, right? So maybe you can make use of a conditional expression here. If let's say value remainder 2 equals to 0, then this value, otherwise 0. So this will actually make sure that only even values are actually accumulated, and in this case we expect the outcome total to be 6. Only 2 and 4 would be added. So you can see the outcome is 6. Now let me I want to create the vector of this type object, point 2D type object. So we have call it p2d vec, and we maybe initialize in the beginning like this. So point 2d, because we have the constructor for this type, so we can make use of this constructor to set the data. So 1 2 and point 2d 3 4 5 6 7 8. So I think we have 4 points here. I think that should be sufficient here. So, and okay, now if I want to do accumulation of these values and get a new point, I mean I want to, like we did the accumulation of 1 2 3 4 5 in this example. I want to accumulate this point so that this x values are added, y values are added. So in that case we want the result of this accumulation to be of point 2D type. So it's going to be point 2D object 2D equals to and beginning value, initial value, we cannot give this number. It has to be the type of same point 2D. So maybe some default initial value, point 2D object with x and y set to 0. So here, and since we have this initial value, like in this case we had this 0 and then integer type, in this case we are going to have both point 2D type. So constant 2D, call it sum, and constant call it value. And you can do return sum plus, right? You can do this operation, but if you want to do this operation, then this addition has to be enabled for this type by overloading that plus operator. Or you can also, if you don't want to do that, then you can create an object temporary equals to sum. When you do this kind of you create an object like this, then it will actually invoke a copy constructor. So if your type does manage the pointers, then you have to have this copy constructor well implemented for this kind of assignment to behave properly. And then tmp temp dot x plus equals to dot x, temp dot y plus equals to value dot y, and then you return temp. Right Now we have this total TD, and we can display it total 2D. Right, this is the way you can implement it. Oh, I think there's an issue here, so let me go back and try to fix it. So the thing is that I try to access X and Y directly, but they are private members. So these are private members we cannot access directly. So if you either you make this structure make it public, or you want to have, say, getter setter functions. So set X int X is a double X, call this px, X equals to px, set Y double py, Y equals to py, and also getter double get X, let me put in a single line to make it appear more concise. Double get Y, return Y. So we can make use of this setter and getter function here. So value dot get X, and get Y. You want to add this to the temp set X temp plus and set Y plus value dot get Y. Right, I think this should work. Let me try it again with this. So we have this total 16 and 21. 16, 21. Let me go back and try to make sure that we have it is accurate. So 16, 21. This, if you add this all this thing X values, 7, 5, 12, 13, 14, 15, or 16, and this 8 and 6, 14, 19, 20, 21. So this 16, 21 that has been accumulated as expected. And accumulation can also be used for different purposes. For example, if I want to compute, let's say, these values but in this form, in the string form, let's say 1, 2, and then let's say plus 3, 5, plus 5, 6, plus 7, 8. So if I want to, if I consider this as the outcome of from the point 1, and then we want to accumulate this with the outcome of point 2, and then we can accumulate outcome from point 3, and we want to accumulate like this. If we want to get this sort of output, then we can make a small change to this. The type where we want to get is going to be the constant character pointer, but it will be more convenient to get a string type object in this case instead of this constant character pointer, this object. So for that, let me just copy and paste this thing and try to make changes to it. So the type is going to be std string. We need to give a different name to it, to the, let's say, 2, and the point, the beginning, the starting point is not going to be point anymore. It's going to be a string type, so maybe some default insert string, which should be empty string. So empty string object, and here this should be a string type, because it is the type of this first parameter should be the type of this thing that is accumulated. So we're going to have string. Now here you create a string object instead of temporary, I mean point 2d is going to be sum, and then you actually add things to it. Temp plus equals to you want to add this thing, and you want to add plus maybe string, and we have numeric value. You need to convert that into string. Is going to be value dot get x. This is this will as convert to the string and concatenate it, and then plus your concatenate comma after that, and then plus, let me put in a different line, plus std get y, and then plus y. So this is the thing that is added to this summation, and if we want to put this plus, then maybe you can put plus here, and you return temp, right? So one thing is that this plus will be even added at the end here. So if you want to avoid that, you have to think about some way of skipping this character. So, and it will now display 2d2. So assignment operator mismatch, maybe I've missed a semicolon. Let me go back. Yeah, it should be have a semicolon here. So you can see this concatenated 1 2, this first point plus second point plus third point plus fourth point, and so on. So but it is just displaying these things. So if you want to display only 1.0 1.12, I mean limit, maybe I encourage you to think about that. Maybe you can take that as an exercise, try to see, maybe consider, I mean you can just I can give a hint that you can consider. Maybe try to think of using something called string uh, string stream. It's a Is it string stream or what is? Let me just see, check. String stream. Yeah, this you can if by using this, I think you may be able to avoid that thing. But I will leave that for as an exercise for you to practice. So next thing we want to talk here is reduce. This is improved. This is basically a accumulation function, but it is an improved version. It allows it has some constraints, and it allows the use of something called execution policy, which I'm not going to be discussing in this recording, but that policy, through that policy you can choose either to execute this algorithm as a sequentially, or in parallel, or in a vectorized way. But I will just demonstrate how you can use it, right? So if you want to use this reduce, then here we have these things, this string type and point type. You can see we say that these are the parameters are of a heterogeneous type, right? So let me write the term. You cannot have this. It's I mean, if you use heterogeneous type, then you have to. I mean, it can complicate. And this type for this reduce can complicate. So you have to be a bit careful when you're using this type. Different types for this parameters. So if you have a similar type, like in this case, then you can use reduce, right? So if I let me just copy this thing and try to um, change it to reduce. So let me I want to reuse this, so remove the type here and reduce. So, and you don't need to do anything here, and I mean you don't need to change anything, just as you reduce and it will do the same job that we had through this accumulation. I think that was not the correct library. Maybe this is SStream or something. Maybe I encourage you to check that library. Something like this, right? So I'm commenting this out. You can check yourself. So this has been computed as before, right? Reduce. I mean, it does the same thing. It does the accumulation. It does summation. And you can also consider using reduce for this array, for this computation. Now, next algorithm I'm going to be talking is inner product. Inner product is an operation that is used in algebra. So in matrix computation. So if you have two vectors like this 1 2 3, and you have another vector 4 5 6, the inner product is basically 1 times 4 plus 2 times 5 plus 3 times 6, right? It does compute this thing. So from this operation you can guess that inner product will receive two containers or two ranges. It needs uh, we need to supply two ranges into it. Let me have for that I need to create another let me create another container. We have this vector container, and let me create another list container. I have to make sure that I have list library included. So we have p2d list point 2d. Let me use 5 6 7 8 9 10 11 12. So this is the list. I will use these two lists to compute the inner product, right? So here for inner product I need to supply the iterators, beginning and end iterators from the first container p2d vec dot begin and p2d dot is vec or vect. Let me just, yeah, I think it's this is vec, not vec. So dot end, and you also need to supply the beginning vector of another container. So p2d list dot begin. Begin is sufficient, and is not needed, and assumption is that this list has at least I mean more than or equal to the number of elements of this first sequence and first container. So now here what we do is like in the case here, you need to supply the initial value, but in the inner product the thing is that what you compute depends on the I mean what this inner product will return will depend on how you compute it, right? So sometimes it could be object, but if I actually want maybe I want to define inner product as, let's say, I mean 1 times 5 plus 2 times 6, and then plus 3 times 7 and 5 times 8. So if I want to define inner product like that, then I can do something like this, right? So the value it will return is going to be integer value of which and double value, I guess 0.0, and So you can supply two things here. This is the initial value, because when you are doing inner product, you are essentially doing accumulation like this. And for this operation, you can define this operation. Either you can supply the lambda expression, or you can also make use of one of the template class template that is available through the functional library. So std, if I want to do the summation of this items terms, then I can use plus like this. And this operation for this, because we have this the elements are of the type with members x and y. So the members would be something like this. We have first member, let's say 1 2, and you do product this with let's say in our case 5 6, 1 2 and 5 6 and 5 6, right? How do you define that multiplication that happens between these numbers, right? So if you want to define that as some product with dot product between these two things, so 1 times 5 plus 2 times 6, this would be 1 unit, and then you accumulate these things across different elements, and then plus like this. So if you want to do that, then I think it would be convenient to define this as an operation in the class itself. So let me have a function here. A function that will return double type, and call it dot. It will receive call it p. It will actually return x times p dot x plus y times p dot y. So we have a constant object, unst constant. So this will return that thing, right? So and then we can do accumulation of these things there. So now here we want to have a lambda expression which will essentially return that result of that operation dot. Call it p2d, and I think you need to have two items here. Let me call this p1 and p2. Const 2d p2, p1 dot p2. So these things, the outcome of these things is going to be this entire thing, and then this operation is applied on these things. So now we can return something double value. So call it return value, and you display it. So let us check this. Let me put it in different line. So this was 356. I presume this is correct. Maybe you can cross check, but probably this is a correct value. I'm not going to go ahead and check and verify it for the interest of time. So next algorithm we want to talk here is transform and reduce. So transform reduce is it is a version of something called map and reduce pattern. If you have dealt with big data or you have some experience in big data, you might have heard this term called map. This is a pattern or method which is a key concept used in big data processing or parallel or distributed computing. It's kind of similar to that, and transform is sort of mapping, and reduce is kind of reducing. So it's kind of I mean, you can see this as a combination of the STD transform that we discussed, and I did discuss this in the previous recording on algorithm topic, and reduce is this function, and it is a kind of combination of combined packaged form of those two operations together. So transform reduce. So let's see how to use it. So again, you want to supply these values. Let me consider this. First, you need to first you need to define what is transformation, right, and what is reduction. So if the transformation, let's say, is like in this case, that you can see this transformation, this operation as a transformation. Or for example, if you, let me just explain it a bit further. So if I have vector, let's say 1 2 3 4, and if I consider transform as this operation, which will actually compute the square of this values 1 4 3 9 or 4, or 9 and 16, or it could also be you want to compute 2 times the value, right? So that is the transformation, and the reduction is to take the summation. So 16 9, in this case 16 9 25 plus 4 29 30. This process is called reduction, right? You add these transform values. So again, here you need to first supply the iterators, and you are actually reducing. For this reduction will demand you to also provide the initial value. The value is going to be integer type, so you supply in this case I think yeah, I think you can assume this is integer, and then again you want to specify what operation. This reduce will require you to have this kind of operation. Either you can make a lambda expression, or you can make use of this tool, and then you put it here, and then finally you can have this lambda expression, but that's going to be a little bit different, because if you're not going to have two containers here, there's only one, you want to work in one container, so let me have only one parameter, and you want to do dot product with itself. So basically what you will be doing through this lambda expression is you have this 1 2 and 1 2 1 times 1 plus 2 times 2 4. That is the operation you are doing for this I mean 2 times 2D data. But in the case of 1D data, it would be something like this. You could receive integer type, and then you return the square of that integer type, x times x, and the value you return is going to be maybe maybe try to reuse this and see whether it works or not. So looks like it is working. This is the outcome. So here again, just to repeat, in the context of the map reduce, transformation is basically a mapping operation. You are mapping from let's say this data to the square of that data, or there could be some different operation you want to use I mean for mapping. So basically it is a mapping operation, transformation. Next things we want to talk here is LCM, or these are actually the tools, utilities available through numeric libraries. So they are useful in, for example, if you want to do something, for example here you have dot, but if you want to do accumulation of GCD values, greatest common difference divisor, sorry, greatest common divisor, least common multiplier. So for that let me create a vector of integers. I think I already have an integer vector, so this one. So if I want to do accumulation of maybe I should consider a different example, but that vector may not be suitable, so I would have a different vector for this purpose, integer, call it I vector, and 24, that's a 60, 36 and 48. So first let me consider GCD, and then I'll talk about LCM afterwards. So this is the greatest common divisor. For example, in the first case, if we consider only 24, its greatest divisor is itself 24, because you can divide it by 24, right? So first initially you can consider this 24 as a divisor when you are dealing with the first element, and then when you move on to the second element, then you have to find the divisor between this 24. Then GCD will actually determine that value. For example, if you use std between, let's say, 24 and 60, and then right, so let me have a few more lines, right? So we have GCD of 2460, and then you want to use that value, GCD between the next value 36 and between this result and the next value 48. And also let me display GCD of only one. I think this GCD receives two values. So in this case, let me see what output we can see here, right? 2460, and then the result of that 2460 and 36, and the result of that entire this thing, and then 48. So it is 12, right? So let me go back to the code. So what actually happens is you assume that GCD in the first case is 24, and then you actually do compute GCD of this thing and add to the previous one, and you compute the GCD of that previously computed one and add to it. So that is how you actually compute greatest common divisor amongst all these values, right? So you implement that. You can implement that using a combination of accumulation and yeah, by using GCD as a utility to it, right? So dot begin and and you supply the initial value. We have considered initial value 24, so you can supply, let's say, IVEC to 0, and if you are supplying this, then you don't need to consider that in the iterator. So maybe you can start from 1 here, and then so we have two things, int a, int b, because in the first case the a will be this thing, kind of sum and the value, and the second element and for this element will be considered a and b. Then you return std of a and b. So it will carry out this operation, and in the next step a will carry the result of this operation. So entire thing, this thing will be in a, and then b will have 36, so it will carry out this entire operation, and it will continue that way. The result is going to be call this different name and display it. So this is the GCD value computed by that accumulate algorithm. Now let us do LCM, lowest common multiplier. So we can follow the same approach, but the only difference would be we use a different utility here. So let me copy everything and paste it here, and I want to compute LCM. So LCM is 720 and GCD is 12. Now next I will talk about midpoint. This is a utility used to compute the midpoint between two numbers in the container elements, or you can say average of two numbers. So it was actually introduced in 2020 standard. So if you use 17 compiler standard and in numeric library, so if you use 17 compiler, it will not compile, and this will be an error. You can use as follows, call it MP midpoint value, two and 7. If you have integer value, it will actually do the integer computation. So if there's truncation happens, for example, if the fractional part will be truncated, in this case 9 by this is 7 plus 2 equals to 9 by 2, 4.5. So this 0.5 will be truncated. If you don't want this to be truncated, then you need to cast this elements to double type. And you can make use of this midpoint value to compute to carry out different things. For example, I have this container. If I want to, if for example, if I have sorted values in the container, then if you want to find approximately median value, then you can use the first element, last element, compute midpoint. It's a median value. Or if for example, let me take a little bit different example here. So if I have, let's say, IV1 equals to 12, 24, 36, 68, another vector IV2 equals to 15, 22, 16, 99. And if you want to do create a new sequence with the element equals to the midpoint value of this elements, right? And this operation can be useful in many cases. Just this is for demonstration. Then you want to define a target sequence of the same size and you can use transform ib1 dot begin, ib1 dot end, and ib2 dot begin. If you remember, just I mean, if you don't remember, go and review this transform function, and then target. Let me call it target, not target. So we have two things here, int x, int y, and we return midpoint of, because x will carry this value and the y will carry this value. In the first iteration, in second iteration, x will carry this value, y will carry this value. So you return midpoint of these two values. Now you can display print container. Let me display all containers. Print c ib1, print c ib2 with a new line character. Make sure that we have a new line here. And here. Now you can see I'm compiling with the 17 standard, so it is complaining. This was introduced in 20 standard, so I need to upgrade to 20 standard to use midpoint. So I mean, this was the first container, second container, and this is a midpoint. So 13 is midpoint between 12 and 15, and 24, 22, 23, 16, 36, 26, and 68, 99, 83. Let us learn this algorithm through coding. In the mutator category, I could find only one algorithm called iota. If you know any other mutator algorithm from numeric library, let me know in your comments. I will really appreciate that. As usual, I have this code to begin with. So this is a type which I'm not going to be using in this explanation, but I will be using this in the next explanation or explanation of next topics. So I will be keeping it here, and this is the function I'm going to be using to display content of a container, and I will be using a container of this type to explain it. So the thing I'm going to be explaining here is the function called iota. So this is the function that is available through numeric library. So we have a numeric library included, so we are good to use it. And this is something that does kind of mutation. It mutates the container in its place. So more specifically, it actually fills a specified range in a container with sequentially increasing values, right? For example, if I have this 1, 2, 3, 4, 5, I already have this container filled with increasing values, right? But if container is empty, for example, let's say, let me clear this container. First display the content, print c, I back, and then new line characters, just to make sure that these two outcome of these two print statements do not get printed in the same line. So let me quickly check the output of this statement, particularly output of this print function invocation and this invocation. I expect this vector, after clearing up this vector, doesn't have anything, so we should expect nothing displayed by that particular statement. So we have compilation and execution. So in the first case it was displayed 1 2 3 4 5, and in the second case we don't have anything. So going back to the code, so here now I want to set the size of this vector to, let's say, 10. I can use this function. So now we have a vector of size 10, and if I want to actually populate or fill in all the elements of the container with increasing value, then I can make use of this function iota, right? So we can do using this syntax. I mean, you want to specify the range you want to work with, either from 2 3 4. Let me, in the beginning, let me start with let me work with all the possible elements or entire range of the container. So begin I bake end, and you want to tell or you want to specify here in this place which value you want to begin with, right? If you want to begin with 0, place 0 here. If you want to begin, that means the first element 0, and then next 1 2 3, so on. So if you have 0, and it will actually populate the elements with this value 0 1 2 3 4 up to the maximum possible value. So if you want to have the first element 1, then it will fill with 1 2 3 4 and 5, right? It goes that way. So we are supplying this first value, the beginning value, to be 0. Now after that we can print and see what happens. So now you can see this it is filled with 0 1 2 up to 9. This tool has many usefulness when it comes to working with the numbers, numeric data. I will consider 3 cases here. One application for this tool would be if you want to create let's say a value, let's say a sequence of the squares of integers, or if you want to create the sequence of the some values power raised to power some integer number, right? Or if you want to create even numbers, in that case first you want to create this all these sequences, and then you can transform these sequences to to get those desired sequences, right? For example, once you have filled in, then you can you can do transformation. So let me just write what we want to do here, creating sequence of let's say a square, which is going to be 1 4 9 16 and 25. These are the squares of integers. So you can do transformation. After you create this sequence, then you can do the transformation, and then I make and target you can write into the same vector, and then how you want to do the transform. So int x, so it should be transformed to the square, and then we can print it. Right, so let us see the output. So now you can see the square values 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Similarly, you can also create a sequence of x raised to power 2, x squared, or x raised to power 3, or something like that. Or it's also possible that if you have a different container, then you can also create a even numbers, sequence of even numbers. But to create that, and it's you need to have this sequence created first. So for that purpose, this function is useful. And another uses of this tool is for creating for finding the indices of specific elements of container, or position of the specific elements in the container, right? For example, let me in this container, if I want to find the index corresponding to, let's say, I think I have this container has already been modified. So we have after and it was modified, we have let me just I'm copying from the output editor, output terminal, the values that we obtained just before. These are the values that were actually generated. So if I want to find out where does the value, let's say 16, let's say 16, 36 and 64 are actually placed in this sequence, right? So the question is where are 36, let's say 16, 36. Let me consider only two values are placed in the container. So for that I actually need to create the indexes first, because I want 0, 1, 2. If you want the position, if you want the first position to be identified by 1, then you can use 1. If you want the first position to be identified by 0 value, then you can use start from 0. But you need to create for that purpose I cannot reuse this container. I need to create another container. So let me create another container called maybe I bake, maybe call indices int, then and I want this to be of the same size of IVEC. Now I want to populate this with the values from 0 to the maximum value. So I use iota, and I start from 0, right? Now after that we can use a function algorithm, for example for each to find the index, let me just display, because for each will not return the index, so I'm going to be displaying it. So let me iterate ivec dot begin and ivec dot end, and the thing I want to do here is I want to receive int x, call x, and I want I actually need to actually capture this, because I want to use this inside. So let me capture this int, and for I can use, I think, for each inside. Let me try for each, but internally I want to use index, right? So ind dot begin, ind dot end, so again we have integer y, call it y, and if I think I have to do a little bit differently here. So in the outer loop I want to place this index, and I will capture ivex and try to use it. So let me make a little bit change here. It's going to be index, and we receive index here, and what we do inside is something like this. So we actually want to use ivec x. So we also want to have, let me have another container, and let me call this found indices, and we want to capture this as well, but we want to capture by reference because we want to make changes. Let me call this indexes. So now if we capture now we capture ivec here. So if ivec dot x equals to, we also need to have the values we want to find, right? So if we want to have these two values, then maybe we also want to have maybe a vector of values equals to 26 and 36. If and we need to capture this values as well, and values, then if this is just for the sake of simplicity, I'm going to have only one value, just to minimize the complexity. So let me have int value equals to 26. one at a time. So I capture value, and if this is equals to value, then I actually insert this this x into found indices. This is vector found in indexes, and we have found indexes, push back x. So after that we can print. Let me see. I hope I don't have problem. Let me try to compile and run. If there's a problem, I'll come back and try to fix it. So print it should be print D. Print C, sorry, print container. So it is not printing anything. So let me go back, and we have yeah, 26. So this is one of the value. No, we have to have the valid value, maybe 16 and 36, right? So 16. So the position is 4, right? So it's 0, 1, 2, 3, 4. So we can find out the index where that particular element is placed, right? If you experiment with 36, you should get 5 and 6, 6 as a position. So this is one of the usefulness of this function. And the third usefulness would be if you want to create a unique IDs. If you want, if you have a software and you have a software with different people, and you want to create unique IDs, then the idea is you can populate a vector or container. Obviously ID, you would want it to be integer. It could be different type as well, but if we are looking at integer, then you can use this function and set ID. For example, if the ID is to be set something like this, let me use it again here. So first I want to clear it, and if you want to get, let's say, generate, let's say, 1000 IDs, and you want the ID to be in certain range, let's say beginning from 1001, then it will actually populate this vector with the values 1001 to maybe 1000 times more, right? So in that case, each element is going to be unique. So you can pick one element from this vector and assign ID to the particular person or particular student or particular member if you are creating a group. So this is another application. There are many other applications you can think of, but I'm just limiting to these three possible application of this function, iota function. Now let us learn these algorithms through coding. As I told you earlier, these algorithms manipulator are for picking the objects from a container, creating new objects and writing them into a new container or range basically. So we consider these algorithms: adjacent difference, partial sum, inclusive scan, exclusive scan, transform inclusive scan, and transform exclusive scan. As in the previous case, I have this code to begin with. I have this point type with attribute x and y, and default custom constructor, and setter and getter functions, and dot product. This is a function for displaying the data, and this is a function for receiving a container and displaying the data belonging to its objects, which is separated by a space. And we have some few containers already created. So with this, I actually want to demonstrate the use of first the first algorithm is adjacent difference. So this is an algorithm to find the difference between adjacent elements in a container or in a range. So let us do it. If I consider this vector, I mean this is a simple vector to demonstrate it in the beginning. So if I want to see the adjacent difference, for example, would be 2 minus 1, 3 minus 2, 4 minus 3, 5 minus 4. So I would use this function as follows. As a difference, then and where you want to write. So for that, let me create a container. Let me select a different container than I have used before. It is a forward list. So to use forward list, I actually need to include the library. For integer type, I call it integer forward list, and I want it to be the size same as ivex size. Now the target is going to be forward list. Then after that we can print it, print the ivex, and print ifls. It should be print C. Just that is my mistake. So let me go back, try to fix it. Should be print C. So we have a function name print C, so we are actually using this function. And I also want to make sure that they are printed in different lines. So this is the adjacent difference, right? 2 minus 1. First, it picks 1. There's no difference. So first element is 1. So 2 minus 1 is 1. 3 minus 1, 1. 4 minus 1. Sorry, 3 minus 2, 1. 4 minus 3, 1. And 5 minus 4, 1. but this is just a subtraction, and this operation you can choose. So it allows you to choose the operation. For example, if you want instead of taking the difference, if you want to do multiplication, then you can specify that here. So this is the library. This is the function operator that is available through the function. I didn't have that library, so first I actually want to get the error with it. Let me see whether I can get error, then I will come back and include that library here. So try to compile. So it is looks like that is already included directly indirectly through other inclusions, so I didn't need to worry about that. So now multiplication is happening, right? So first we got 1, 2 times 1 2, 3 times 2 6, 4 times 3 12, 5 times 4 20. So this is based on this operator, it will do the, and basically it is designed by default, designed to take the difference, but if you specify different operator, it would apply that operator to the adjacent element to create a new sequence. Now if we want to apply this for these containers like this, in that case let me try using for this container vector point 2d, which has point values with x and y 1 2 3 5 5 6 7 8. So the name of the container is p2d back dot begin, and where you want to write, like in this case you need to specify where you want to write. Maybe I actually want to write in this container, so it will actually overwrite to the element. The size is same, 4 elements. Then just do like this, right? So print c p2d pc, print c p2d list. So it is complaining, right? So the complaint is that looks like that subtraction, it does by default, it does a subtraction difference, so that operator is not defined for that particular type we're working with. So the type of the element of this container is point 2d, and looks like that operation is not defined here, so it is looking for that operator. So you can define that result of subtraction is going to be the point 2d type. So you return this object, then operator minus, and then constant 2d p2d. Again, this is a query, and you do create a temporary object equals to, we want to subtract from this object to the current object. So p2 create temp, and then temp dot x equals to p2d dot x minus x, temp dot y equals to p2d dot y minus y. return 10, right? So with this I think we should be able to run. So this is a subtraction operator defined, and we have this application of adjacent difference. So comparison successful. Now subtraction carried out. Perhaps I should have inserted new line character, so let me just do that so that we can analyze this result better. So we have new line character, we have new line, so this is the result of subtraction. So first element is second. In the second it was subtraction from this first element to the second element. So 1 minus 3 equals to minus 2, 2 minus 5 equals to minus 3, and 3 minus 5 equals to minus 2, 5 minus 6 equals to minus 1, 5 minus 7 minus 2, 6 minus 8 minus 2, right? So subtraction is happening in a reverse way, right? So from this what we should understand is that, that we should have implemented this operator in a reverse way, right? Something like this: x minus and y minus, this way. So you have now 3 minus 1 2, 5 minus 2 3, 5 minus 5 minus 3 2, 6 minus 5 1. So this is the difference, like we have in this case. And if I want to apply multiplication, if I want to multiply like this, then what happens? Let's see. So it is still complaining, and from the message that we have, it looks like this multiplication operator is not defined. So you need to define that multiplication operator. I mean, you need to overload that multiplication operator for that particular type. So we need to have this operator, something similar to this. I mean, in terms of this, I mean, the the signature line, only the difference would be multiplication, and you may decide, I mean, the way how you want to define the multiplication of two vectors, right? So if it is point by point multiplication, then you can define like this. If we, I mean, usually we expect the result of this multiplication as a this output, but if you want to define, let's say, inner product, then it would be different, right? So you would be returning a value, scalar value, and that actually not that will not directly work in that particular case. So we have x multiply x, y multiply y, and that thing is returned by this operator. Compilation, and then we have a result multiplication, right? So this is the 3 times 1 and 5 times 2 10. So 5 times 3 15, 6 times 530. 7 times 5 35, 8 times 6 48. So one thing I need to mention here is that in the output, I'm just copying the output from the terminal, bringing it into editor to help explain it better. So if you want to see only difference, for example, if you are not interested in the first item here, so you want to see the difference between these two things. In this case, we have implemented multiplication, so multiplication or difference between these two things, then you will not be interested on this thing. So if your interest is only on the difference, then you may want to remove the first element, right? But if you remove the first element, then you will be losing information. So if you don't care about that information you are losing, then it is okay to remove this first element. If you do care about that information that you lose when computing the adjacent difference, then you want to keep the first element. You don't want to remove the first element, right? So if you want to remove that first element, then you can do something like this. You can use the erase function, let's say either in a vector, erase the beginning element, right? Or you can also use, let's say, pop. You can also use pop front if that your container supports that. Pop front, that will actually extract that element, remove element. So this is also one approach, or you can also use erase. Or for this second container P2D, so after erasing we have this container values printed. So again we have typo problem. Going back, I think it's, what is it? Well, yeah, we have a problem here. So you can see these three things. I think this is maybe I choose a different container, right? So wrong container. Let me go back. So I should have chosen this target container here, and this target container to remove the element. So So the list for yeah, for list doesn't support this erase function. So maybe let me try to use a pop front in this case. This is we have used forward list, so uh, it may not be even able to support this pop front. Let me try it. So it looks like it's working. So we have this these things. We have removed this first element if not needed. Then we have the only differences, and here also we have only differences kept in the container. Next tool or function to discuss is partial sum. So partial sum is basically it is it's also called, another term for this is running total, or it can also be called a cumulative sum. Right, for example, if I have let's say 1 2 3 4 5, and its running total would be first 1, and then you add 1 and 2 and 3, and then you add 3 with 3, and then you have 6, you add 6 for 10, and you add 10 5 15. So this is going to be the thing that is going to be computed by this function, right? So we again use IVEC, this container, and we also reuse the list, maybe resize this list, I mean, because we have already removed one element here, so maybe dot ifls dot some dummy value, and use it ifls dot begin, right? So print C, so looks like this editor was not displayed. Let me just quickly explain what I did. So I actually wanted to demonstrate the use of partial sum, so which is also called running total and cumulative sum. If we have a container with these elements, and the partial sum would be, let's say, addition of, I mean, first element is going to be first element, and in the second element of the partial sum would be addition of the current element and the previous element of partial sum, and here it is the addition of this value and this value 6. So here it is addition of this value and this value, and here addition of this value and this value, and this resulting thing is called partial sum. So we want to compute partial sum of IVEC, and since ILFS has been reduced by 1, we did a pop front, so Therefore I actually wanted to enter one extra element into it, so that the size will become equal to the size of IVEC, so that we can use this as a target container. So, and we have a print statement to display this vector and IFLS. Clear. Pushback is not supported, so maybe we want to use push front for this. So we have so again I should have, I mean, same problem, so I should have placed this character here. So you can see this is these are the values, and we have partial sum 2 plus 3, 3 plus 3 6, 6 plus 4 10, 10 plus 5 15, right? So this is the partial sum computed. If I want to do this similar operation for this vector, so again we have removed one element, so we want to increase the element for the list. P2D list dot, you can, I think we can use pushback here. Let me use front. It has to be P2D object. This is just dummy value. It's going to be replaced, I mean rewritten, so it doesn't matter what data you put here. You have adjacent different, but you need to name change the name to partial sum. And we just want to do summation, not a multiplication here. Then after that we print these things, right? So let us see it in the output. So this is I mean again the same problem. It is complaining that this summation is not, operator is not defined for that type, because in the previous case we used the integer. So I mean integer summation for integer is I mean it is defined with the compiler itself, we don't need to do anything. In this case it will try to do addition, like in this case these elements are added, but here it will try to do addition of these point to the objects. So we need to define that operator here. We have subtraction, we have multiplication, but we don't have addition. So for addition we can just copy this, paste, and change this minus to plus, and this minus to plus. So this is the addition operator, and we have partial sum invocation. So you can see the summation 1 2 1 2 here, and then this is the summation of this data and this data. 1 plus 3 4, 2 plus 5 7, 4 plus 5 9, 7 plus 6 13, 9 plus 7 16, 13 plus 8 21. Now the next thing to discuss here is uh, a version of the function, a function which is pretty much kind of similar to this, but a little bit more features or more advanced version of this, which is std inclusive scan. This is a function which is similar to partial sum. You can say it does the exact operation as a partial sum, right? So, but some features, it supports something called execution policies. Such as parallel. These are the examples of the policies. For sequential execution, and this is for right, and you can also have it's going to be pair underscore. So different policies are there. So but I'm not going to be demonstrating the use of these policies, but just I wanted to highlight the difference between partial sum and inclusive scan, right? So let me comment this out. I'm going to be copying this partial sum and changing this to the name of the function to inclusive scan. Right, so we'll see the output is going to be different. Same as before in the previous case. So you can see maybe let me go back to the code. So we have this things displayed, this things displayed. Maybe save. Maybe I forgot to save the file. Again, back to the terminal, and yeah, you can see here the same thing displayed. So it does the same thing, but the difference here is that you can apply these policies. You can pass this other of these policies the first argument, and that is you are actually asking the algorithm to consider policies for this particular function. This policy is actually defined in the library called execution. So you need to include that library on the top. Just I wanted to demonstrate. I don't want to go in detail about that. Execution. So essentially the same thing. The policy is different policy actually only implement how the computation is carried out, but uh, final result is going to be same. Only the difference would be if your hardware, uh, if the computer where you are running your software supports different execution policies, then uh, parallel execution policy will execute faster. This policy will actually make it execute faster. Sequential may take more time, right? So that would be the difference, but I'm not going to be discussing this here more. So Next function to discuss here is kind of similar to this inclusive scan, but it actually does exclude. For example, if it does scanning, I mean does this accumulation, it actually excludes the first element, so it will be 1, and then for example it will exclude 3 from addition to compute this value. It will exclude 6 from addition to compute the value placed to be placed here. It will exclude this 10 from the addition, no sorry, it will exclude this value 2 in the computation to be placed in this place. It will exclude this value 3 to be used to get the computation to be placed here, so it operates that way. Therefore we call that as a exclusive. This is a previous one is inclusive, and the new one is exclusive. So in the exclusive scan, there's one small trick, a problem you need to consider. For example, if you don't provide this initial value, then what is going to be used in the beginning, right? So you need to provide some initial value to be used here, because I mean it will take one as initial value and copy that, but usually, but if this is not allowed to be used, and how it would compute the value for this to be placed here. So you need to provide some initial value, so that value is going to be placed in this place. So it could be some I mean small value, or it could be some whatever value your application requires. In this case we assume that initial value is 0. No, it would be in the case of the integer, but in this case I mean we are working with point, so point 2d, and initial with 0 and 0, x and y 0, right? So this could be the initial value here. We have this is let me change this inclusive to exclusive. So let me quickly demonstrate the output of this newly added part of the code. So this was the output. Previously we had the initial value, but since we have supplied initial value 0, so initial 0, and it is added with the previous value, but this current value is not used in addition, so we don't have this value included in this computation. And here these two are added, 1 2 3 4 are added and placed here. This is not included. So 3 plus 1 4, 5 plus 2 7, so this is excluded, and to compute this this is excluded. So we have 5 plus 3 plus 1 9, and 6 plus 5 plus 12 13. So that is the only difference between inclusive scan and exclusive scan. Now the next thing to be discussed here is I mean the versions of this inclusive and exclusive scan, but with the transformation combined, right? So first I will talk about transform inclusive scan. This is kind of similar to a mapping and reducing approach that I discussed in one of the previous algorithms. Or you can see this from the perspective of, let's say, map reduce pattern that is widely used in big data processing. So we can use this transform reduce using this syntax, pretty much similar to what we have done here, but with some few changes. Let me use integer now to demonstrate this integer container, and I want to write in the iterator list. We have here we have used this integer vector and integer, this is integer for list. So now here we want to have two operations. One is let's say reduce operation. How do you reduce? One is let's say transform, mapping or transform operation, right? So separated by comma. So this reduce operation is something like, basically what you want to do is you want to do transformation to this element and do the summation with the previous one, and you transform. For example, if you want to do summation of the squares, the computing square is going to be transformation, and computing the summation is going to be reduction, reduce, right? So if we want the reduction to be the addition, then you can specify like this: addition plus, and transformation, you can it could be you can specify transformation through a lambda expression. If, for example, if you want to do squaring and then and summation, then we have x return x times x, right? So this is the transformation, this is the reduction operation. So we'll get the transform and inclusive scan. So let me copy those statements which were actually used to print this two things. I think here we have these two lines and use it in this place, right? So to the terminal, looks like something is missing there still. Did I miss? I just copied and pasted. Line number 132. I think I missed a semicolon here. Go back. So this was the result of transform and reduce. For example, you have 1 2, right? So transformation applied is a square, so 4 plus 1 equals to 5, right? And so this is a 9 times 9 plus 5 equals to 14. We have 16 plus 14 equals to 30, and 25 plus 30 equals to 55. And the operation is happening as we would expect. So this is a transform inclusive scan, and we also have this version for exclusive scan. In that case, it will just skip that the current position object. So let me copy everything to demonstrate this. No change. I think like we had we need to provide the initial value, so we also need to provide initial value here, but in this case we are considering integer container, so the initial value to be supplied would be placed here, and we provide initial value to be 0. So we have, you know, it is I mean first element 0, first I mean 2 is excluded, so 1 1 square plus 0 1, and 3 is excluded, so 2 square plus 1, 2 square plus 1 square is 5, and 4 is excluded here, so 3 square 9 plus 2 square 4, 9 4, 13 plus 1 square 1 14, and 5 is excluded, so we have 4 square 16 plus 9, 25 plus 4 29 plus 1 30. Okay, it is working. I don't see any issue with this. I think that is all about this.